Engineering geologists are the guardians of our infrastructure. They analyze sites to mitigate risks and ensure safe design. Through sustainable development, they protect lives and build our future. Welcome to ACoreConcept, your knowledge-sharing channel. Subscribe to our channel for beautiful minds and great ideas. Click the subscribe button and turn on notifications. Thank you for supporting us.
Welcome to this explainer. Whenever we see a massive suspension bridge, a towering hydroelectric dam, or a high-speed tunnel cutting right through a mountain, it's almost impossible not to marvel at the sheer engineering of it all. But today, we're going to look a little deeper. Literally, we are exploring the hidden foundation of modern infrastructure and the unsung heroes who actually ensure our survival against the raw, totally unpredictable power of nature. They are the guardians of infrastructure, engineering geologists. I absolutely love this quote. An engineer builds the structure, but an engineering geologist ensures the mountain doesn't take it back. It perfectly sets the stage for the central conflict we're looking at today. It's human engineering versus the immense living force of the earth. Think about it. An engineer can calculate the exact load-bearing strength of concrete and steel to absolute perfection. But honestly, it doesn't matter how incredibly strong your concrete is if the mountain beneath it suddenly decides to shift, slide, or collapse. The mountain always has the last word. For a classic example, look no further than the Leaning Tower of Pisa. It's arguably the world's most famous geotechnical failure, and a pretty comical historical lesson in what happens when you build a heavy, massive structure on soft, poorly consolidated soil without truly understanding the geology of your foundation. It's a mistake modern builders literally cannot afford to make, especially not in the extreme, high-stakes environments we're building in today. So the crucial takeaway here is that these professionals aren't just out there casually looking at rocks. An engineering geologist acts as the vital bridge between geology, the earth, and engineering, the structure. They are essentially interpreters. Their job is to diagnose the literal mood of the mountain. They look at the unique character of the rock. Is it fractured? Is it weathered? How is it going to behave when we decide to drill a massive hole right through it? They are the only ones who actually know how to listen to what the ground is telling us. To make this dynamic even clearer, let's contrast the two roles. While the civil engineer is focused on man-made materials, your concrete, your steel, building up into the sky, the engineering geologist is entirely focused on the natural materials. They're looking down, they are mapping fault lines, assessing rock mass quality, tracking subsurface fluids, and figuring out how to build down to secure that foundation. They answer the absolutely critical questions of where and how to build safely, well before the first shovel ever hits the dirt. Now, let's turn our attention to the ultimate testing ground for these professionals, the Indian Himalayan region. We have to remember that unlike the highly stable ancient rocks you'd find down in southern India, the Himalayas are alive. Because the Indian and Eurasian tectonic plates are continuously smashing into each other, this is the youngest and most tectonically active mountain chain on Earth. It's a highly volatile antagonist in our story, filled with sheared, folded, and incredibly fragile geology. It is literally still rising as we speak. And dealing with this mountain range is basically like fighting your way through different boss levels, with every specific physiographic zone presenting a unique, deadly geohazard that has to be navigated. Down in the sub-Himalayas, you're dealing with poorly consolidated rock that practically invites massive debris flows. Move up a bit to the lesser Himalayas, and complex geological folding triggers massive landslides. Push all the way into the higher Himalayas, and you're facing the terrifying prospect of rock bursts brought on by immense mountain weight. So how do they actually handle this? Let's dive into decoding the living mountain and the specific methodologies they use. They achieve this through a really rigorous, multi-step methodology. First up is the site investigation. This involves deep subsurface drilling and geophysical surveys to see hundreds of meters below ground before moving an inch of dirt. Then comes geotechnical mapping. They use complex characterization systems like the rock mass rating, or RMR, and the Q system to mathematically quantify just how good or bad the rock actually is. Finally, they run a comprehensive risk assessment, actively identifying deadly geohazards like flash floods or hidden seismic faults well before any construction kicks off. Now, let's look at how this plays out in the trenches, securing tunnels, dams, and roads. There is a vivid, terrifying contrast between a successfully supported tunnel and the absolute devastation of a collapse. This really highlights a brutal phenomenon known in the industry as squeezing ground. This happens when the rock mass is just too weak to withstand the extreme stresses created by excavating the tunnel. the mountain literally tries to heal the wound, squeezing inward and crushing the excavation. Without a geologist accurately predicting this and designing a flexible support system, the results are catastrophic. Which brings us to this staggering number, 1,000 plus meters. That number represents the immense overburden pressure sitting right on top of deep Himalayan tunnels. Imagine a full kilometer of solid rock pressing down on the empty space you just hollowed out. This crushing weight frequently triggers explosive, deadly events called rock bursts, where the actual rock wall violently shatters inward, almost like a bomb going off. This is exactly why, in massive, complex projects like the Atoll and Zogella tunnels, the engineering geologist is the one dictating what support systems will keep that 1,000-meter mountain from collapsing in on everyone. Based on their real-time rock mass calculations, they decide literally inch by inch whether to use sprayed concrete called shotcrete, deep rock bolts, or heavy-duty steel ribs. They also have to constantly monitor the mountain's behavior as massive tunnel boring machines inch forward, making sure the machine itself doesn't get completely trapped by shifting ground. The stakes are just as incredibly high for hydropower projects. In Indian Himalayan states like Uttarakhand, Himachal, and Sikkim, hydropower is quite literally the backbone of the economy. Here, geologists are absolutely vital for ensuring the foundations of massive dams won't suddenly slip during a heavy monsoon season. They also study deep geological folds, like synclines, to predict and manage sudden, massive water ingress, which are essentially hidden underground rivers that could instantly flood an entire tunnel or an underground powerhouse. And above ground, the challenges certainly don't stop. For highways and roads, especially vital economic lifelines and massive pilgrimage routes, like the Char Dham Yatra, geologists have to calculate what's called the factor of safety for steep mountain slopes. They meticulously design slope stabilization reinforcements, using techniques like soil nailing and retaining walls to manage debris flow, secure the drainage, and prevent massive landslides from burying the roads and the people traveling on them. So, what is the ultimate payoff? Let's discuss the triple value and why we desperately need them. Their value really comes down to three main pillars. First, safety. Their primary non-negotiable job is to prevent disasters and save human lives. Second, cost efficiency. Let me tell you, it is drastically cheaper to study a mountain for 6 months than to spend 6 years fixing a collapsed tunnel. They prevent the geologic surprises that totally bankrupt projects. And third, sustainability. They ensure infrastructure doesn't trigger man-made landslides. And crucially, they make sure the natural groundwater springs that local villagers completely depend on aren't accidentally destroyed during the excavation process. Now let's look at the ultimate geohazard challenge, the Himalayan boss level. We've already talked about the continuous tectonic uplift, but these geologists also have to design around major active fault lines, like the main boundary thrust, which regularly trigger huge earthquakes. Add to that the very modern crisis of climate change. Melting glaciers and highly erratic monsoons mean geologists now have to predict and protect structures against glow-offs, glacial lake outburst floods. These are massive, sudden walls of water and debris. So they are constantly adapting to dynamic, shifting threats that change year by year. It's time we recognize the hidden infrastructure heroes of our modern world. The reality of the situation is we all see the towering bridge, we drive through the deep tunnel, and we admire the perfectly smooth concrete. But we rarely, if ever, see the massive, incredibly detailed subsurface geological report that made it safely possible in the first place. Without their meticulous translation of raw, wild nature into hard structural data, none of these multi-billion-dollar infrastructure projects would survive their very first year in the Himalayas. I want to bring it back to this concept. We don't conquer the mountains, we understand them. Engineering geology isn't just an optional luxury or a simple box to tick off on a permit application somewhere. In volatile places like the Himalayas, it is an absolute necessity for our economic security and our physical survival. Engineering is all about building, sure, but engineering geology is about where and how to build safely. I want to leave you with this final thought to ponder. As climate change continues to intensify and our global infrastructure needs push us further and further into fragile, completely untamed terrains, are we truly prepared to respect and understand the geology beneath us? Or are we just going to repeat the arrogant mistakes of the past? The living ground is always talking. We just need to make sure we're sending the right people to listen.